Right, where was I? Metrizable space. We want the covering dimension to be finite. And let alpha be a minimal homeomorphism. These are standing assumptions. So this whenever I write X, I mean such a space. Whenever I write alpha, I mean a minimal homeomorphism. And under these conditions, the cross product C-star algebra is classifiable. Of course, these conditions are a bit stronger than necessary. Instead of finite covering dimension, we could ask for mean dimension 0 of the homeomorphism, but I want the covering dimension to be finite. Okay, so that means in this sketch, this kind of C-star algebra, or these kind of C-star algebras take up a certain amount of space in here. So they're always going to be stably finite because they always have traces. And notice that I did not draw this line around the AF algebras or the Yang-Su algebra. For the reason for that is the next theorem. Of Robin Dealey, Ian Putnam, and Karen from 2020. So if X has finitely generated K-theory, alpha is minimal, then there exists a natural number D and finite abelian groups F0 and F1 such that Kj of the cross product is isomorphic to a direct sum of Z to the D with Fj, where of course J is either 0 or 1. Now let's call this star, because now comes the opposite direction. For any natural number D and finite abelian groups, you can find a space and the minimal homeomorphism such that star holds. So such that you can find a space and a homeomorphism such that the cross product has this K-theory. Now this tells us in particular that AF algebras and the Yang-Su algebra are not included in here because they have vanishing K1, and that's not possible here. It says for I think it says for any D, and yeah, sure. Sure. Thank you. No.
Well, okay, so
oh, okay. So
this is actually unclear.
Oh, right. Yeah, whether n contains 0 or not.
You can't kill like in the cross product. You have the unitary, and you can't destroy its
K-theory
class, right?
I think so. Yeah, I think that's the point.
Yes, but that is unfortunately not universally agreed whether that symbol black bold n contains 0 or not.
Right. So I guess for me it doesn't contain 0. Yeah. Okay. So yeah. Right. Yeah, so how can we do better? I mean, I guess the point is that these C-star algebras are super nice, right? Like they're very well understood, but apparently a lot of interesting C-star algebras cannot be realized as such cross products. So how can we do better? Meaning, how can we modify this construction so that we are able to construct more C-star algebras while at the same time keeping it tractable? Now that leads me to the next definition. Take two open subsets of your space, then a partial automorphism is a homeomorphism which I will always denote by theta, going from U to V. So what happens is we have our space, we choose some open subset and some other open subset, and then theta is supposed to be a homeomorphism from U to V. And just like in the global case, we can obtain a Z action by taking powers. Okay, so obtain a partial Z action by taking powers. Theta to the n. But now, if we do that, we have to be a bit careful with the domains because, well, if I take let's say I take a point in U and I map it to some other point using theta, if that other point is not in U anymore, then I cannot apply theta again. So even though this point was in the domain of theta, it's not going to be in the domain of theta squared. So what we would like is that this point gets mapped into U again, so into the intersection of U and V, and then you can apply theta again. I'm just going to say beware of domains. Now let me give an example of a partial action. Let's say we start with a global homeomorphism. And then we choose a closed subset, Y of X. And we basically take this set Y out of the domain of the action. So we define theta to map from X without Y to alpha of X without Y. And X should just get mapped to alpha of X. And we start with something global and we restrict the domain. Okay, so this is like the most important case for us in this talk. Okay, so now what you can do if you have an action of a group is you can form the cross product. And this also exists in the partial case. So we can form the cross product, the partial cross product. Now I won't define now what this is exactly. I will later outline a more general construction, which includes this as a special case. Yeah, but anyways, so now you can ask under which conditions are these C-star algebras classifiable? And this is what the next theorem says. It's the theorem of Shirley-Geffen from 21. if you take a minimal partial automorphism, and again, we want the covering dimension of the space to be finite, then the partial cross product is classifiable. Okay. Now how, I mean, that means somehow we can add it to this sketch, but how exactly? So the next theorem. Oh, thank you for the question. It means basically the same as in the global case, that you don't have any invariant subsets, but you need to be a bit, yeah. So how do I remember how this?
You'll say the cross product is simple.
Sure. That, yeah, that's equivalent. Yeah. So I guess minimality would be that, like, so we call let's say y is a, let's not say y. W and x is. Sorry again?
If you compare this node, then everything is minimal. If there is no
Nothing is minimal.
Right, because you still want the, so one of the equivalent conditions is that the orbits are dense. Yeah, so yeah, maybe that's the easiest. Well, not necessarily. I mean, if an orbit is finite, it's not going to be minimal by definition. I mean, okay, minimality requires that yeah, you need that's the thing. So you need u and v to be dense in order for this to, like, if it's not dense, then it's not going to be minimal. Right. Yeah.
But so is this any proportion that we call it dense?
Yes. So I guess that's the easiest definition to state.
So infinitely far either forwards or backwards.
Yeah, exactly, right. Yeah, so you can have orbits which stop somewhere, but then they have to.
But if it starts
Yeah.
positive time, it has to go infinitely far negative.
Yeah, exactly.
Such a partial exists.
Like in general, like on any space, or
I mean, sort of my mental picture is like that thing that you've done on the board there, which is very far away from you and V both being dense and all orbits being in at least one direction.
right.
If I try making or like putting some closed set,
Mhm.
again, I'm thinking about like putting a region of the circle under irrational rotation, which is not good.
Exactly. No, but
So what does have this problem?
right. So an equivalent, if you want to look at this example, an equivalent definition, equivalent condition to the resulting partial action being minimal is that this set y meets every theta or meets every alpha orbit at most once. So y, you're not allowed to intersect orbits more than once. So for example, if you take the irrational rotation on the circle and you just take out one point, then that would be an example where the domain stands. And, yeah. So oh no, u and v are the domains. So
Yeah.
what you take out is like the complement.
Okay.
Yeah.
Yes,
Yeah.
I see. I can just go with you. Okay.
Right. Thank you.
X minus one.
Yeah.
Yeah, so maybe I should have said this. So this is u. And this is v. Okay, so the next theorem tells us something about the Elliott invariant of these partial cross products. From the same paper of Robin, Ian Putnam, and Karen. Take two countable abelian groups. and a showcase simplex delta with finitely many extreme points. Then there exists some space and some closed subset of that space and a minimal homeomorphism. Such that, so let me write A for the partial cross product to save some time. A0 of A is isomorphic to Z direct sum G0. K1 of the cross product is isomorphic to G1. And the tracial state space is isomorphic to delta.
You want alpha or theta partial data?
Sorry?
Your A as theta, but there is no theta in your
Oh, yeah, sorry. Okay, so theta is this, theta is like in this example. So you have your global homeomorphism alpha and you have a closed subset. So yeah, theta is this thing which goes from X without Y to alpha. Yeah, thank you.
That's also supposed to be minimal.
Well, it will be if Y satisfies the right condition. So if Y meets every alpha orbit at most once, which which it does, like this set you get is has
Yeah,
this
okay,
property,
but
then
here it says there exists a sexual Y.
yeah, but this Y will have the property that it meets every alpha orbit at most once, and so the
No, that's not what I mean. Given G0 or G1 and delta, as you define X, you define closed subset Y, such that whatever it is, and you then should insist that the Y meets each orbit at most once.
yes, yes. Otherwise this wouldn't be simple. The
Yeah.
thing you get wouldn't be simple. Right. Yeah, so I want to update the sketch. So now somewhere in here we have the partial cross products. Yeah, now they include AF algebras and the Yang-Su algebra because of this theorem. I'm drawing a dashed line. As far as I know, there's no like definite result on the range of this, or like no restriction on the Elliott invariant. Maybe someone else knows better. So they might actually be everything in the stably finite setting, because again they always have traces. So yeah, they're always going to be stably finite. Yeah, so as I said, I'm not going to define it right now, but later I will like define something more general, which includes this as a special case. So yeah, then I hope it will be a little more clear.
In the case of this particular situation, the deleted set Y,
Uh-huh.
is this the same as the
Yes, I believe so, yes. Yeah, so right, this includes the orbit breaking. Yeah, so now that brings me to my next point, because now so far we've only been in the stably finite setting. So what about the purely infinite case? How can we construct purely infinite C-star?
Are they going to be uniform?
Yes, if the space is compact. Because if the space is compact,
Oh.
because still C of X sits inside of the cross product. So yeah.
Domain of theta equals X. That's the point.
Again, sorry.
The domain of theta to the 0 power is all of X.
Yeah, exactly. Exactly.
Has anyone considered the non-compact?
I mean, you can define it without problems, and you can also, yeah, you can define the partial cross product, but I'm not sure if they were studied in this setting in terms of, yeah, I don't know if that exists.
It's crazy that the spaces are not compact. So it's kind of crazy. What's problems? Well, there are lots of non-unital classifiable elements. In general. It's true that when you say, well, I can think of one problem, it's not clear what you mean by T of A. Because T of A is normalized on the unit. Yeah. But certainly the general classification theorem includes non-unital algebras as well.
Okay, so yeah, let's talk about the purely infinite case. And to be able to construct purely infinite C-star algebras, we will add another piece of data. And the other piece of data we add is a vector bundle. So take a partial automorphism on a space X. And now also take a vector bundle over the domain of the partial automorphism. This should be a rank n vector bundle. So just to make sure we're on the same page about what the vector bundle means, I mean that the E is the bundle space, it's a topological space. This thing is a continuous surjection. For each point in the base space, if you look at the fiber over that space, so the pre-image of the point under the bundle projection, this has the structure of a n-dimensional complex vector space. The n is this n from here. And also it should be locally trivial. So for each point in the base space, there exists a neighborhood of that point such that if I restrict the vector bundle to that neighborhood, or equivalently, if I take the pre-image of the neighborhood under the bundle projection, then this is isomorphic to the trivial bundle over the neighborhood. And now we can also talk about sections of the vector bundle. The section is a continuous map from the base space into the bundle space, which is a right inverse to the bundle projection. So basically, if I start at some point in the base space, then the section will associate to that point a vector in the fiber over that point. And then if I project back down using the bundle projection, I have to end up at the same point. Okay. So let's consider gamma naught of A, which is the space of continuous sections vanishing at infinity. And this is a right Hilbert C of X modulo. So it's a C of X module, which also has a C of X valued inner product. Now that means we need to define this right multiplication by continuous functions, and we need to define the inner product. Basically, everything is defined pointwise. So if I take a section and a continuous function.
X is no longer compact.
No, X should be compact, but the vector bundle is over U, and U is an open set.
Oh.
So yeah.
Right.
So then the section multiplied with the function, if I evaluate it at some point, this should just be scalar multiplication in the fiber. So xi of x times f of x. F of x is a complex number. Okay, and the inner product is defined also pointwise. So if you take two sections, then this, for each point in the base space, this is going to give you two vectors in the fiber over that point. And we can take the inner product in the fiber, which gives us a complex number. So we have a complex number for every point in the base space, which gives us a continuous function. Of course, you have to choose the inner products in the fibers in a continuous way, but you can do that because it's locally trivial. Yeah. So now we have a right Hilbert C of X module, but we want a C-star correspondence. What we need for a C-star correspondence is a left action. So define a left action. i.e. goes from C of X to the adjointable linear operators on the Hilbert module. So these are the adjointable linear operators.
Always been fascinated by the fact that besides not being grammatical, adjointable has 4 syllables, whereas with that it has 3 syllables.
Yeah. Yeah. So you need to ask for it to be adjointable, because if you have a bounded operator on a Hilbert module, this is not automatic anymore, like for Hilbert spaces. But in the other direction, if it's adjointable or if it has an adjoint, then it's going to be bounded automatically. Okay, so how is this left action defined? We take a continuous function and we apply it to a section. Then this should be right multiplication, but composed with the action. So the left action on the Hilbert module is how you incorporate the partial automorphism.
Adjointable is a word, but that doesn't mean what you want it to be.
Okay, so right, so now we have a C-star correspondence. Over C of X, which we denote by curly E. And we can take its Cuntz-Pimsner algebra. Which we denote by O subscript E. Now, I don't really have time to define in detail what how a Cuntz-Pimsner algebra is defined. I'm just going to say how I think about it. I don't know if that's a good way to think about it. Well, this is like the universal C-star algebra generated by C of X, so the C-star algebra, over which we have our C-star correspondence, and the C-star correspondence itself. So for us, the sections with certain relations. So for example, you want that if you, for any two sections, take the adjoint and multiply it with the other section. This should be the same as the inner product of the sections in the Hilbert module. Okay, so maybe it becomes more clear if I give some examples. First of all, take alpha to be a global homeomorphism. And as a vector bundle, take the trivial line bundle, x times c. Then the Cuntz-Pimsner algebra is isomorphic to the cross product. Now, why? Well, we can think of the cross product as the universal C-star algebra generated by C of x and some unitary implementing the action with the relation that f times u is equal to u times f composed with alpha, right? Now, if you look at what the space of continuous sections of this vector bundle is, it's going to be isomorphic to C of x. So up to right multiplication by continuous functions, all I have to care about, the only section I really have to care about, is the constant section taking 1 everywhere as its only value. Because every other section I can reach by right multiplication with a continuous function. And this constant section is going to give you your unitary. So we can see from where here that it's going to be in isometry, because this inner product is going to be the identity. And then you have to show that it's also unitary. And this condition, where the action comes in, is exactly how we defined our left action.
C of x is commutative. You need to emphasize it. Gives you a right view of the model.
Oh, I mean, what do you mean? Like,
if the ring is commutative, then it's, you don't need to emphasize the model is right or left.
right, but then you define a left action. So I guess, like, if you would take a, I mean, I guess the standard definition of a C-star correspondence is that you have a right module and you have a left action by adjointable operators. I guess you could also define it the other way around, right? Like to have a left module. I mean, I guess you could switch everything, but you have to decide, right? I mean, they're not interchangeable. The action is different from the right multiplication because
So it's going to have one action on one side and not action on the other side.
right, but
You could, since the algebra is commutative, and you switch the whole business around, you'll get the same thing.
okay, but a bimodule would also be one where you have a left inner product, right?
You have to have them acting on opposite sides. If you don't, you have to specify that the two actions commute. If you have them acting on different sides, then that's automatic. I mean, it's part of the
Yeah, so it's all read like a bimodule.
Uh-huh. Yeah, right. But I want to emphasize that we only have a right inner product. So just an inner product on one side. So the inner product does not have to be compatible with the left action. Yeah, so for so here, if you take two sections and you multiply from the right with a continuous function, you can take it out of the inner product. But not for the left. So if you have, let's say, e of f applied to psi eta, this is not the same as taking it out, as taking f out. Okay, next example. If theta now is a partial automorphism from some open set U to some open set V, and E is the trivial line bundle on U, on the domain, then the Cuntz-Pimsner algebra is the partial cross product. So if you want to, you can take that as the definition of the partial cross product, since I haven't defined it before. Yeah, but that would be a possible definition. And the last example, if your space is just a point, then of course the vector bundle is trivial and the action is trivial as well. So you can, all you can do is take the trivial rank n vector bundle over the point, and then the Cuntz-Pimsner algebra is the nth Kuntz algebra. Again, why? Well, the space of sections of this vector bundle, the section is just a vector. So if you choose any orthonormal basis, this is going to give you n orthogonal vectors. And now from this condition, you get that there are isometries. And then you also have to show that the range, the sum of the range projections is 1, but you can show that.
If we're looking at the section that vanished at infinity,
Mm-hmm. Right.
that also is probably.
Oh, but then, I mean, if the space is compact, then you don't need to worry about that, right? Like C of C0 of x is the same as C of x if x is compact. So it doesn't. Exactly, yeah. It's nothing to. Yeah, right. So vanishing at infinity means that for every epsilon, you can find a compact set such that outside it's bounded by epsilon. But since it's compact, yeah. Okay. I need to.
I just have a question about what might be given towards it seems to me in the two theorems of giving examples, if you like, give already examples of what can occur. The variant is not calculated completely. It's just certain aspects of it. For instance, in the first case, the trace. I don't think you mentioned the trace simplex.
Yeah.
And the order of and pairing. You're not mentioning the pairing. Well, in the last example, you're not mentioning the pairing. Just the.
Yeah. So I mean, it might be that there are more results, but I just didn't write them down. Maybe Karen knows more.
Oh.
It might be that I have just omitted some results. I don't exactly remember. I just didn't want to write so much. But yes, I'm pretty sure that it doesn't.
If someone wants to know why you're going for more examples, then you'd like to know how exhaustive the examples are that have been mentioned already.
Yeah. So I mean, that's a very good question. I guess the motivation at this point for this example is to have purely infinite C-star algebras, because all of those are stably finite, right?
So you're sort of leaving the finite case to the finite.
Yeah, exactly. So thank you. Yeah, so this is basically what I wanted to say next. So I mean, you can see here this kind of example. It includes the partial cross products, which we had before, but it also it's also able to produce purely infinite things.
Okay.
The Kuntz algebras.
But it does include the case considered before. Maybe it's more extensive. Maybe it does consider. Maybe it doesn't give you an infinite dimensional simplex. Maybe. There's a question of the extent of the example, and also just what the precise information is. They're ranked in the K0 and the basic, well, that's exactly the same as the order. The order of the
Turning this sort of all pretty generative. It just looks at the first what you said there on K0A. That's all it is.
Yeah, I didn't quite catch that, but you're okay, but then you're, I won't, okay, so there are, there's no what the total invariant is,
You can construct examples that have this property. You don't know when so great variant.
And so I'm saying the theorem should say that given G0 and G1, delta and so on, and with the specified pairing, the pairing acts in the obvious way on the first direct sum, first direct summand G0A and kills everything in G0, whatever it is. That occurs. And AF algebras up there don't occur because of this theorem and because of Giordano Pascal, whatever it is action gathers.
Thank you. So I would delete that if it's okay.
Or anybody else have more questions about it?
Does the bundle construction give you more in the finite case and give you more than?
That is a very good question, and it's certainly something that we might look at, but we're not there yet. Okay, so it's already a bit later than I planned, but anyways. So now again, we can ask about classifiability of this example. Oh, sorry, yeah. That's a theorem of Maria Stella Adamo, Don Archie, Maziforo, Magdalena Georgescu, Ya Young, Karen, and Grazia Viola. Three, which is concerned with the global case. So if alpha is minimal and E is a vector bundle. Yes. No, because it's 7 people, so I didn't.
Oh, yeah, right.
Don Archie, Maxi Coro, Vanilla Chase.
Oh, my goodness. Well, this is you. One thing. I wondered how you knew so.
And yes,
Yes.
Okay, so under these conditions for a global action, global Z action, this is classifiable. And now it's either it's either stably finite, if n is equal to 1, if you have a line bundle, or it's purely infinite if n is greater than 1. Okay, and now comes the theorem, which is basically summarizing my the first year of my PhD. So let's just say the previous theorem still holds if we replace alpha with some partial automorphism. And the vector bundle should also be over U then. Okay. Replace alpha and E. Okay. Yeah. So now, of course, to prove that it's classifiable, you need to check a number of things. Separable unital nuclei and satisfying the UCT is clear, basically, because it follows from general properties of Cuntz-Pimsner algebras. There's not much work to be done there, but you need to show that if the action is minimal, then the C-star algebra is simple, and you need to show that it's Z-stable. And I guess the easiest way to do that is to show that it has finite nuclear dimension, using that the space has finite covering dimension. Did I write this somewhere? Yes. Yeah. Okay. So I in the last, I don't know, 5 minutes, I guess, I want to very briefly outline how to show finite nuclear dimension. Okay, so it's basically the same as in this theorem of this paper of Shelley-Geffen. What you do is you decompose the underlying space and the action to reduce to the case that your action has only orbits of a fixed size. So the cardinality of the orbit should be m for all x, and for some m. And under that condition, the orbit space so yeah, the space you get if you quotient out orbit equivalence. This is Hausdorff. So yeah, I should say, so up to this point, it's almost the same as in this paper, but like proving finite nuclear dimension in this case is different. That's the point. Orbit space is Hausdorff. So let's say pi is the quotient map. Then you obtain a map pi star, an embedding from C of x mod z into C of x. These are exactly the functions, continuous functions, which are constant on orbits. Sorry, so the image of this embedding are the continuous functions constant along orbits. And so this is, if you look at how the multiplication is defined, if f is constant along the orbits, then this theta just vanishes. So this is going to be contained in the center of the Cuntz-Pimsner algebra. Okay, so that means that the Cuntz-Pimsner algebra fibers over the orbit space. It's a C of x mod z algebra, and the fiber is OE. So if you evaluate that at some, so a point in the orbit space is an orbit. So if we look at the fiber at some orbit, this will be exactly the Cuntz-Pimsner algebra of the C-star correspondence restricted to that orbit. So that just means, well, I mean, we have our orbit with a fixed size, or we only have orbits of the same fixed size. You just restrict the vector bundle, you restrict the action. So then, of course, the vector bundle is trivial because it's over a discrete set. So this is the same thing for all points because all orbits have the same length. And it's simple and finite dimensional. So it's just going to be some matrix algebra. And then we're done because, well, now we have a continuous field of C-star algebras. Each fiber is a matrix algebra. And now you can, just going to write that down here. You can bound actually the decomposition rank. This is less or equal than this. Take the supremum over all fibers, the decomposition ranks of all fibers. +1, -1. This thing is 0. This is bounded by the covering dimension. So this whole thing is bounded by the covering dimension of the space. Yeah. Okay, so I should stop. I just want to say, yeah, this is how far we've come. now, and now I guess the next step would be to look at the Elliott invariant of these system algebras. Okay. Thank you.